fait plaisir aujourd'hui d'accueillir John Ruan de l'Université du Bishop. John a fait son doctorat à l'Université de Washington en 2017. Ensuite, il a eu un poste de chercheur postdoctoral à l'Université McGill. Et John s'intéresse aux objets compacts et en fait à ce nouveau monde de l'astronomie des ondes gravitationnelles qui est absolument excitant. John, en fait, a une chaire de recherche du Canada en mécanical astrophysics. Donc aujourd'hui, on va parler des objets, des contreparties avec ondes gravitationnelles. John?
Thank you. So some of you might be looking at this image and thinking, oh, this is a JWST image from the PSF. But in fact, well, you might wonder what this thing is. That's actually not real. It's actually a simulated galaxy that I grafted onto this image. But I use this as my title slide because I think it nicely summarizes what my talk is going to be about, which is when you look at this simulated galaxy here, this is a merger of two galaxies, and these galaxies have supermassive black holes at the center. And when they merge, they will emit gravitational waves that we can emit. And I'm very interested in studying what the sources of gravitational waves look like from electromagnetic emission. So when we detect gravitational waves, we point our telescopes. What do they actually look like? What can we actually learn from these sort of systems? So that's what this is. Okay, so next. Okay, so gravitational waves come with a whole wide range of frequencies. So you might be most familiar with high frequency gravitational waves. So this is high frequency, low frequency. High frequency gravitational waves are detected by LIGO. And because frequency scales inversely with mass, these high frequency gravitational waves come from the mergers of low mass objects. So stellar mass black holes, stellar mass neutron stars, right? So these are merging neutron stars, merging stellar mass black holes. For more low frequency gravitational waves, they come from more massive objects. So these are, for example, mergers of supermassive black holes at the centers of galaxies. So when galaxies merge, we get this binary supermassive black hole system, and that's what's illustrated here. My talk is going to be in two parts. First, I'm going to talk about what we can learn from gravitational wave detections of binary neutron star mergers, and then I'll talk about what we can learn, how we can detect the host galaxies of supermassive black hole mergers that are detected in gravitational waves. Okay, so for the first part of my talk, I'm going to focus on the question of what is the origin of the heaviest elements in the Milky Way? And the answer to this question actually it's related to gravitational waves, right? So when we look at the periodic table, we know where most of these elements come from. For example, from stellar evolution. But near the bottom of the periodic table, it gets a lot more messy and a lot more uncertain. So for example, these lanthanide elements right at the bottom of the periodic table, it's been a mystery for about 60 years what the cosmic origin of these lanthanide elements are. And there's been a lot of theories. It's been long debated. For a long time, people have thought that, oh, they actually come from neutron star mergers. So when you have two neutron stars that are in a binary system, they will eventually merge through gravitational wave losses. They lose angular momentum and they merge. And in that merger, you actually produce heavy elements, and I'll talk about why that is. But this is not for sure, and there's a lot of other sort of models, right? So these are sort of exotic core collapse supernovae, like these collapsar systems where you get a accretion disk around the newly formed black hole at the center, where you get a core collapse supernova. There's these rotational, rotationally driven supernovae. These are more exotic types of the core collapse supernovae. And it's not at all clear which of these possibilities is actually the origin of the heaviest elements. So, for example, for binary neutron star mergers, there's a lot of reason to believe that it can't be binary neutron star mergers, because in order to get a binary neutron star system, you would need this enrichment from a binary neutron star system would come from pretty low redshifts, because you would need to first form a binary neutron star system. So you have two stars that go supernova and form two neutron stars, and then it takes a long time for them to merge. So this would happen at pretty low redshifts, for example, in our galaxy. But when we look at the stars in our galaxy, it turns out that what we see is that the heaviest elements in our galaxy are formed at pretty high redshifts. So it doesn't actually seem it's actually not clear which of these is correct. Okay, so a lot of the questions were answered in 2017 when LIGO detected the first binary neutron star merger in gravitational waves. Right, so these are two binary neutrons. These are two neutron stars in a binary system. They lose angular momentum through gravitational waves. They merge. They fling out a lot of neutron-rich material, and that's called a kilonova. Okay. There was also a gamma ray. It also shot out a relativistic jet. That's called the gamma ray burst. I won't talk about the relativistic jet. So this was detected first in gravitational waves. So this is the this green. This is the sky localization in gravitational waves. So this green is the sky localization that was detected by LIGO, and the Fermi Gamma Ray Telescope also immediately detected, about 2 seconds after the gravitational wave detection, detected a gamma ray burst from this same region of sky. So that's the red here. And a lot of ground-based telescopes pointed to this part of the sky to see if you can actually identify what the host galaxy is. Do you actually see anything? But of course, there's a lot of galaxies in this region of the sky. So just along, I accidentally pressed something, just along sort of this localization region here. This is the zoom in, and all of these dots are different galaxies. So telescopes pointed at each of these galaxies, and in one of them, they found this transient, which is shown in the crosshairs here. So that is a new transient that was detected in the localization of this gravitational wave event. And it turns out, so the telescopes followed up this new transient over the next weeks or so. And this is not a light curve. This is actually an SED. So this is wavelength here. So this is the UV, this is the infrared, this is flux. This blue curve up here is the early time emission, and then this red stuff down here is the late time emission. So you can see the SED was bright early on, and it was very blue, and then later, about a week after this gravitational wave event, it faded and then it got better. So the SED moved to the IR, and you can see this sort of behavior in spectra as well. So people also got optical IR spectra. This is flux, so this is the early spectrum, and you can see it's pretty blue, and then it faded and got better. So the interpretation of this event was that this was a binary neutron star merger, and when it merged, you produce this gravitational wave chirp, like as expected. But as it merged, it flung out a lot of neutron star material, which is very neutron rich, and it's this neutron star material that produced the optical infrared emission that you see. So how you actually produce this emission from this merger is through rapid neutron capture nucleosynthesis. So when the merger occurred, it flung out a lot of material, including a lot of neutrons. So there was just a lot of free neutrons floating around. It's a very neutron-rich environment. And there were seed nuclei. So this is a seed nucleus. It doesn't matter what atom this is. This is a seed nucleus. There's a lot of free neutrons floating around. And this seed nucleus can capture these free neutrons. And it becomes a much more neutron-rich nucleus, okay? And the neutrons in this nucleus can beta decay into a proton. So this is some radiation that's emitted during this radioactive decay, and the neutrons in this nucleus can turn into a proton. So once this neutron turns into a proton, you have a new heavier element. And so this is rapid neutron capture, and this is how we think the heaviest elements on the periodic table gets made. Because it's very easy to capture free neutrons because there's no Coulomb barrier, there's no electrostatic propulsion. So you can always just capture free neutrons, and then the neutrons will decay, and then you get a heavier element. And this goes on and on and on until in the ejecta, that's in this material that's ejected, this process continues on and on until you get until you form the heaviest elements at the bottom of the periodic table. So we think that's in this binary neutron star merger that was detected, we formed a lot of heavy elements. Okay, so from observations of this first binary neutron star and only binary neutron star merger that we've detected so far, what we now know is that binary neutron star mergers and this sort of explosion that occurs afterward, it's called a kilonova. Binary neutron star mergers can be one source of the heaviest elements. But a really important question is it the dominant source? Is that where the heaviest elements in the Milky Way come from? Earlier, I told you that there's good reason not to believe that, because for the heaviest elements in the universe, in the Milky Way, we think that they were produced pretty early on in the universe, like pretty high redshifts. But binary neutron star mergers would only occur at relatively low redshifts because it takes a long time for this to happen. Okay, so to answer the question of are these kilonova explosions from binary neutron star mergers the dominant origin of the heaviest elements in the Milky Way? How would you answer that question? Well, how you would do that is to compare the abundance patterns of these heaviest elements from the Milky Way to kilonova from binary neutron star mergers. Okay, so this is the abundance pattern of the Milky Way. So this is atomic number, so light elements over here, heavy elements over here, and this is abundance, right? Now, there's 4 different colors here. Each of these colors is a different star. So there's 4 different stars here. And the lines, each of these black lines are the same. The line is actually the R process, the heavy element abundance pattern of the sun. And the point here is that they all look pretty similar. It's, if you look at stars in the Milky Way, and also including the sun, they all have a very similar abundance pattern of these heavy elements. Okay? So it's a very distinctive abundance pattern of heavy elements in the Milky Way. Now, if binary neutron star mergers are the dominant source of these heavy elements, then the abundance pattern produced in binary neutron star mergers should look like this. So you just, if you can somehow measure or infer the abundance pattern of heavy elements from kilonova, you can directly compare to this and see if they look the same. Make sense? Okay, but that's much easier said than done. How do you actually do this? You can infer the abundance pattern of heavy elements from binary neutron star mergers by looking at spectra. So this is infrared spectra of kilonova from binary neutron star mergers. So this is actually a observed spectrum. So this is wavelength over here, flux over here. The black is the observed spectrum from that first binary neutron star merger I showed you, and this red is a synthetic spectrum from a radiative transfer simulation. So can you do something like this and get an abundance pattern, infer the abundance pattern of heavy elements from a kilonova and then compare it to the Milky Way? So how would you do that? You can use these radiative transfer simulations to get these synthetic spectra and then compare it to the observed spectra. So this is sort of like for exoplanets, the atmospheric retrieval. So this is the radiative transfer simulation we're using. We're assuming that deep down in the ejecta material, it is optically thick, but then there's a line forming region, and that's where you get the absorption lines. This whole ejecta material, unlike exoplanets, this whole ejecta material is expanding relativistically. So there's an explosion, and the radiative transfer it's the radiative transfer simulation we use is one-dimensional, so we assume that it's spherically symmetric, and then we produce synthetic spectra to compare to our simulations, our observations. Note that previously, when I showed you a comparison of observed spectra to observations, that's just forward modeling. So you're taking your synthetic spectrum from radiative transfer and comparing it to the observed spectrum. But we're doing inference, so we're taking the observed spectrum and trying to infer parameters such as the abundance pattern from that binary neutron star merger. Okay, so how we do that is sort of complicated. This is a diagram. Oh, and this is work led by my grad student, Nick Vieira at McGill. Nick's been working with me since he was an undergrad at McGill, and I was a postdoc there, and he continued. He's a PhD student there now. Okay, so these are the inputs over here. There's the algorithm, there's some outputs. So I'll just start with the inputs. So what is input is your observed spectrum of the kilonova. And again, you want to infer the abundance pattern of the heavy elements from this observed spectrum. We also input grids of abundance pattern that are from a nuclear reaction network calculation. So I'll show you that. And then there's atomic line lists. Okay, so what are these grids of abundance patterns? So that's what these are. So these are abundance patterns, right? So these are atomic number on this axis. So light elements over here, heavy elements over here, and this is abundance. And these abundance patterns are from a nuclear reaction network calculation. So that calculates, if you input some parameters, it calculates for you what the resulting abundance pattern should look like. So the abundance patterns, the parameters in this calculation are things like neutron richness, just how many neutrons there are, how neutron rich is the environment. If your environment is very neutron rich, then you can capture a lot of neutrons and synthesize very heavy elements. There's also things like the expansion velocity of the material. When you capture neutrons, that's like a two-body thing. And if your material is expanding very rapidly, then it's harder for two objects to find each other. So that's why the expansion velocity is relevant here. And then there's entropy, which controls things like how easy it is for neutron-rich nuclei to photodissociate. So if you have a nucleus and you capture some neutrons, how easy is it for a photon to come along and knock that neutron off? So that's this is control. And you can see that if you vary these parameters, you can get different abundance patterns. The abundance pattern changes, and so we do these calculations and we input them into our radiative transfer simulation. So that's one of the inputs into our radiative transfer. And of course, you need, since we're doing radiative transfer, you need atomic line lists for these heavy elements. So these are just for one of the elements. What is it? Yttrium, I think. This is the line list. There's this whole forest of lines. Oh, and these are laboratory measured line opacities. They're not complete. However, we did do our own theoretical atomic structure calculation to get theoretical lines as well. Turns out our results are not really sensitive to which exact line lists, because the really important lines in the spectra are lab observed. Okay, so we have our grid of theoretical abundance patterns and our line lists. We input them into our radiative transfer and we get a synthetic spectrum. And now we can compare that to the observed spectrum. So we compare that. So we're basically doing Bayesian inference. It's a little more complicated than that, because it turns out that in the inference, if you're just doing like, a nested sampler or NCMC or something, at every step, when you recalculate the likelihood, you have to rerun your radiative transfer simulation. That's very computationally expensive. So we do some machine learning stuff. I won't talk about that. If you're interested in hearing about that, I can talk about it later. But so you basically do your Bayesian inference and you get your parameters. You get posteriors in your parameters, and then you can. And what's output is the inferred abundance pattern that was produced in this kilonova. You also get best fit synthetic spectra. So the best fit synthetic spectra looks something like this. So there's three spectra here. It's the 1.5. So this is the spectrum at 1.5 days after the merger. That's this line here. Right? It's the observed spectrum versus and as well as the synthetic spectrum. And then there's a spectrum at 2.5 days, which is this line here. You can see it faded and the peak got better. And then there's the spectrum at 3.5 days. And in general, the synthetic spectrum from our fits are a reasonable match to the observations. But what's more interesting, what we're really after, is looking at the inferred abundance patterns that produce this. So this is the inferred abundance pattern from that kilonova, from that binary neutron star merger. So this is abundance pattern. So light elements over here, heavy elements over here, and this is abundance. I'm showing you the abundance pattern inferred at those three different epochs, from those three different epochs of spectra. So in the blue is the inferred abundance pattern at 1.5 days after the merger. So it looks like this. You can see it drops off very dramatically here. And so it doesn't produce all the heaviest elements. At 2.5 days, it actually looks exactly the same. It's hard to see because it's exactly lying on top of the 1.5 days. Okay. So there's also a lack of very heavy elements. And at 3.5 days, you can see that you actually produce heavy elements. So you actually go all the way out, here, well past the lanthanide elements at the bottom of the periodic table. So the interpretation for this is that at early times, at 1.5 days and 2.5 days, when we had this abundance pattern that didn't produce all the heavy elements, that sort of really drops off around here. What this is from dynamical ejecta from during the merger. So when the binary neutron star merger occurred, it flung out a lot of material. It turns out that there is a neutrino wind through weak interactions. The neutrino wind turns the neutrons into protons, and so there's not a whole lot of free neutrons around, and that's why we don't produce all of the heavy elements. But the overall point is that we think the reason why the early emission didn't produce a lot of heavy elements is that it is from this dynamical ejecta that gets flung out when the merger happens. In contrast, this later epoch, this later emission did produce a lot of heavy elements. And what we think is that what's going on there is that what you're seeing at late time is emission from an accretion disk around the final remnant. So after these two neutron stars merge, you formed a black hole. So that's the black hole at the center. And then there's material that was flung out, but some of it falls back in and forms an accretion disk around the black hole. And this accretion disk can also generate winds that blow out material, and that material can also be very neutron rich. And because it's very neutron rich, produces all of these heaviest elements. And these are elements right at the bottom of the periodic table. So at late times, the interpretation is that you have this accretion disk around the final black hole that produces all of these heavy elements. Okay, but the really interesting question is, okay, so we've inferred the abundance pattern from this first binary neutron star merger we've ever seen. How does it compare to the Milky Way? Because that will tell us whether binary neutron star mergers, such as this one, can produce the heaviest elements in the Milky Way. Right? So on this abundance pattern, inferred abundance pattern I showed you earlier, I actually also overplotted the abundance pattern from the Milky Way, which is that this black line. It's actually the solar R process abundance pattern. But I showed you earlier that the Milky Way seems to have a consistent R process abundance pattern. This heaviest elements abundance pattern, they all seem very consistent with each other. And just sort of qualitatively, by eye, you can see that our inferred abundance pattern from this binary neutron star mergers seems to be sort of consistent with the Milky Way. They sort of look the same by eye. And in fact, in particular, it looks a lot like this red stuff, this later emission. And that's actually where most of the mass is, because the sort of total abundance pattern that's produced in this merger is some sort of mass-weighted sum of the early emission and the late emission. But the mass is mostly in this late emission. But it would be nice if we can do this more quantitatively and actually compare. And so we're working on that. What this is, this is some ongoing work by my grad student Elodie at Bishop's. And what she's doing is she's doing a more quantitative comparison between our inferred abundance pattern from this binary neutron star merger to the Milky Way. And so this, what this is showing a histogram distribution of lanthanide fraction. So lanthanides are these heavy elements that have atomic numbers 60 to 70 or so. So these are, you sometimes hear them called rare earth elements. So these elements are pretty heavy elements. And so that's the lanthanide fraction. What fraction of these material, or the heavy elements that got produced is in lanthanides? And what we're comparing is the lanthanide fraction inferred from this binary neutron star merger, which is this shaded region. The error bars are kind of like, and that's from the binary neutron star merger. We're comparing them to stars in the Milky Way, which is this red distribution, as well as a solar. Right? And I showed you earlier that in general, stars in the Milky Way and the sun show this similar abundance pattern of the elements. So that's why they look the same. But the point here is that this this lanthanide fraction in the Milky Way is very consistent with this binary neutron star merger, which is really exciting. The error bars are large, but that's because we've only ever seen one binary neutron star merger. We will observe more and sort of and do this computation, do this comparison more. But the early hints that we're seeing is that these kilonova explosions from binary neutron star mergers can produce the heaviest elements in the Milky Way. Okay, so we just checked the time. Okay, so some takeaway points here. So when we observe binary neutron star mergers, they have these kilonova explosions that occur when they merge. And if you obtain their spectra contain a lot of information, and you can actually infer the rapid neutron capture abundance pattern, the abundance pattern of these heavy elements that are synthesized, produced through rapid neutron capture for individual kilonova. And we've done this for the first binary neutron star merger we've ever seen, GW1717. And what we find is that the inferred abundance pattern seems to be consistent with the Milky Way, which suggests that binary neutron star mergers can produce the heaviest elements in the Milky Way. Okay, I'm going to pause here and see if there's any questions, because I will start talking about something very different.
You know, still the time scale that you mentioned, those happening too late in the
yes. So yes. So what happens with the time scale argument? So there are ways to shrink that time scale. So that's possible as well. But the reason why that time scale is a problem is because the various ways to shrink that time scale are very uncertain.
So it's an interesting model. My only worry is if everything is stuck in a disk, how does it disseminate in the galaxy afterward?
Oh yeah, so so people do As in, like, when this merger happens, how do you, and it generates these heavy elements, how do you like distribute this throughout the galaxy? Yeah, so there are people have done these simulations of galaxy formation where they track how the elements move and get distributed throughout the Milky Way, and things like supernovae will help push stuff out, turbulence. There are ways.
For the abundance point you had, I think on the y-axis there was some negative values on it. I was just wondering to interpret what that means there.
Yeah. So wait, hold on. There's some y values. There's some negative values.
Or no, on the right hand plot.
Oh yeah. Sorry. This is a log.
Oh,
sorry. I relabeled this to make it. Yes.
And this figure on the left, I mean, there's a decent agreement where most of the masses, and it, I don't know, maybe seems to diverge at the heaviest elements.
Yeah.
Like there's less mass, so maybe there's larger uncertainties, but could this mean that maybe there's some process here that would require a more neutron-rich environment to make those heaviest elements?
Yeah,
or-
so we're less concerned about what happens out here, just because this is one binary neutron star merger. How much neutron-rich material gets ejected, and how heavy of the elements, how far up here you get in the subsequent kilonova, how heavy the elements are that you can synthesize, depends a lot on things like the mass ratio of the two binary neutron stars, and the exact masses and things like that. So my point is that different binary neutron star mergers will produce different abundance patterns, and we're only looking at one, right? So this shaded region is only one. This abundance pattern is only for one binary neutron star merger. It's possible that when we observe another binary neutron star merger, they will produce elements out here. It sort of fills in this, but we've only ever seen one, so this is the best I can show you. Yeah.
When you retrieve these abundance patterns, I mean, I guess you don't have full freedom for each individual species, right? But you have certain patterns given.
Exactly.
Can you say a bit about this?
Yeah. So so there is the abundance of each particular atom is not a free parameter, and we're actually using these abundance patterns that I calculated from nuclear reaction network calculation. So for there's only really three parameters. It's not that each element is its own free parameter. Only three free parameters here. But as you vary these parameters, it gives you a different abundance pattern, and that's what we're actually using inputting into our radiation transport.
And can we fully rely on? Can we be sure that these three parameters are covering the full space?
Can we? So yes, we can rely on these free parameters are covering the full space. However, what is uncertain is that there are details of the nuclear physics that are highly uncertain. So in these nuclear network calculations, that they're just solving these systems of differential equations that control, capturing of neutrons, and then neutrons are decaying, and then these nuclei are photodissociating where neutrons get knocked off. There's a lot of uncertainties in rates of like reaction rates, cross sections, even like nuclear masses that control things like cross sections. There's uncertainties there. So yes, there are uncertainties.
I guess what I'm saying is, can you go back to the comparison with the basically retrieval results?
Mm-hmm. Here.
Yeah, when you compare the results, let's say at 3.4 days to the solar hour process. So the fact that, for example, between 80 and 90, there's this big minimum that is coming from your prior in some way, right?
Yes. Yeah. So yes, this is real, and we're inferring that. But yeah, as I was telling you too, we're less concerned because different binary neutron star mergers will produce different abundance patterns, and so. And of course, the Milky Way abundance pattern is a sum of a whole bunch of binary neutron star mergers. All right. Okay, so I'm going to move on and stop talking about the origin of the heaviest elements, and instead I'm going to start talking about lower frequency gravitational waves where you detect binary systems of supermassive black holes. And I'm going to try to answer the question of how do we identify the host galaxy of the first supermassive black hole binary that will be detected by pulsar timing waves. So you may have heard a few months ago that pulsar timing arrays detected the stochastic gravitational wave background, right? So that's a very low frequency. So that's these low frequency gravitational waves that are produced by the local population of supermassive black hole binaries at the centers of galaxies. So in nearby galaxies, in all of the nearby galaxies, there can be binary supermassive black holes, and the sum of their gravitational wave emission is the stochastic background. And that was detected a few months ago. However, over the next few years, pulsar timing arrays will start detecting these gravitational waves from individual galaxies. So not just the total sum, but they're actually going to start resolving individual galaxies and saying there is a binary supermassive black hole somewhere over there from individual galaxies. But how do you identify the host galaxy? Okay, so right, so this is at much lower gravitational wave frequencies where you're detecting merging supermassive black holes from pulsar timing arrays. Okay, so these sort of binary supermassive black hole systems are, we expect pulsar timing arrays to detect them because these supermassive black hole binaries are an inevitable outcome of hierarchical galaxy formation, right? So in galaxy formation, we expect smaller galaxies to merge into bigger galaxies, and when they merge, they have supermassive black holes at their center, and these supermassive black holes will eventually merge and emit gravitational waves. These gravitational waves will be detected at low frequencies by pulsar timing arrays and also by LISA, the laser interferometer strafe antenna. So pulsar timing arrays will won't detect supermassive black hole mergers. They will detect supermassive black hole binaries. So they're still orbiting around each other. They haven't merged yet. When they're still orbiting around each other, the orbital periods are longer, and so the gravitational wave frequencies are lower, and that's what pulsar timing arrays are. In contrast, LISA will actually detect the mergers. And so that's because LISA detects slightly higher gravitational wave frequencies. So when these two supermassive black holes are actually merging, their orbital period starts decreasing, and so the gravitational frequency increases, and LISA will detect that. Right? So binaries, mergers, but really it's I'm interested in both of these things. So when pulsar timing arrays or LISA in the 2030s detect supermassive black holes, mergers and binaries, it's really important to actually figure out which host galaxy that supermassive black hole binary is in. So they'll be able to, these gravitational wave experiments will be able to tell us, oh, there's a gravitational wave source in this part of the sky, but which galaxy is it? And that's really important because you can do things like, for example, measure cosmological parameters, right? So this is your classic Hubble diagram. This is distance on this axis and velocity, recessional velocity. So you can place supermassive black hole binary host galaxies on a Hubble diagram because from the gravitational waves, you can actually get a luminosity distance. You get a luminosity distance from modeling the shape of the gravitational wave waveform. And once you do that, if you can figure out which host galaxy it is, which galaxy in the sky it is, then you can go get a spectrum and get a redshift, and that gives you the recessional velocity, and you can immediately place it on this plot. So each of these dots can be a supermassive black hole binary host galaxy, and you can constrain cosmological parameters. Also, if you can figure out which host galaxy it is, you can turn your telescopes to that host galaxy and study things like circumbinary accretion flows. So if you detected a binary system of supermassive black holes in gravitational waves, and this binary system is in a gas-rich environment, okay, that you can see a lot of interesting effects. So, for example, for circumbinary accretion disks, you expect to excavate this circumbinary gap around the binary just due to gas force, and there'll be people have predicted that there should be mini accretion disks around each of the supermassive black holes. There'll be streams of gas, etc. So you can study these sort of circumbinary disks if you can figure out which host galaxy it is. Finally, you can probe the coevolution of the central supermassive black holes and their host galaxies. So, for example, this is a classic M-sigma relation. So this is black hole mass on this axis, and this is the velocity dispersion of the host galaxy. When we look at galaxies in the local universe, we can see that they lie along this well-known M-sigma relation. Okay, so the black hole mass is related to the velocity dispersion of the host galaxy. We believe that this occurs due to AGN feedback, active galactic nuclei feedback, which ties the growth of the black hole to the growth of the host galaxy. However, to test this, we need to sort of measure this M-sigma relation at high redshifts, not just for local galaxies, but at high redshifts. And that's really hard to do. gravitational waves can help you do that, because from the gravitational wave waveform, you can get a black hole mass. And then if you can figure out which host galaxy it is, you can then go get a spectrum and get a velocity dispersion. And you can place your supermassive black hole binary host galaxies on this plot and do that pretty high measures. So yeah, I emphasize that all of this cool science is predicated on our ability to identify the host galaxy. So you need to be able to identify the host galaxy, but that's really hard to do because gravitational wave localization regions are going to be large. This is a gravitational wave localization region from LIGO, right? And this is from LIGOs, but I put this here to sort of illustrate to you that the sky localization, this is the localization in the sky of the gravitational wave source, can be pretty large. So there's a lot of galaxies in there. Right? And so people have sort of done calculations and simulations to estimate how many host galaxies in the gravitational wave localization region would you expect. So this is a simulated LISA sky localization region. And so all of these, so this is RA in depth, right? Sky position, and all of these dots here are host galaxies. This is a simulated pulsar timing array sky localization region. So all of these dots are possible host galaxies that are in the localization region. And the point here is that there's lots of possible host galaxies, tens to hundreds or so that you would expect. And then the question is, okay, which of these is the actual host galaxy of the supermassive black hole binary that you just detected in gravitational waves? Okay. So how do you actually solve this problem? There's been a lot of work on understanding electromagnetic signatures from the gas-rich environment around the supermassive black hole binary. Okay, so if you have a supermassive black hole binary, it's detected in gravitational waves. It's in a gas-rich environment, so there's a circumbinary accretion disk around it. Then there can be unique signatures, electromagnetic signatures, right? So people have done this sort of simulations, and what a lot of people find is that in these circumbinary accretion flows, there can be periodicity. So that are caused by various gas flows. So you can see, for example, in this simulation, there's this sort of lump that repeatedly gets formed just due to torques. There's this bright lump, and this lump can create a periodicity in the light. So after you detect this supermassive black hole binary in gravitational waves, and turn your telescope to that patch of sky, and you see if there's an AGN there that looks periodic, and that's just because of this what's going on in this circumbinary accretion flow. Okay. People have also suggested that if you have a binary supermassive black hole system that's merging, okay, so it's the orbit has decayed and it's very close and it finally merges. Well, during the merger, it loses mass due to gravitational waves. It's losing angular momentum and mass through gravitational waves, and which means that at merger, the mass of the central supermassive black hole actually decreases suddenly. And at merger, because the gravitational wave emission is not isotopic, there's actually a kick. So the merged supermassive black hole gets a kick. And all of this, combines to cause the accretion disk to shake. Okay? So if you imagine your supermassive black hole at the center all of a sudden loses mass and then it gets a kick, then the surrounding accretion disk is shaken, and this shaking can cause spiral density waves. So this is a simulation of an accretion disk where you have a supermassive black hole at the center, and if you just cause it to suddenly lose mass and receive a kick, what happens? Well, you get these spiral density waves in the surrounding accretion disk, and these spiral density waves can cause a transient, can cause the disk to brighten suddenly. So this is a light wave. So this is time on this axis. This is luminosity, and you can see this. They predict this transient that occurs on timescales of heat circle. So the disk should brighten over weeks. There's a lot of other predictions as well that I've just highlighted two that are easy to understand, but there's a lot of other predictions. However, I'm very pessimistic about these approaches to identifying the host galaxy, and there's a lot of reasons why. So, for example, if you detect a supermassive black hole binary in gravitational waves, and then you point your telescopes in that patch of sky, you might not see anything because the supermassive black hole binary might be enshrouded in dust. Right? So if you have a supermassive black hole binary, even if there's an accretion disk around it, and then it's just enshrouded in dust, you won't see It's also likely that the supermassive black hole won't be strongly accreted. There won't be an accretion disk around the supermassive black hole binary. And just because simulations have predicted that most supermassive black hole binaries and mergers would occur in gas core environments. So all of this stuff that I showed you earlier, where you have this gas-rich environment with an accretion disk around the binary, it's not going to happen because it will likely be in a gas core environment. And finally, the electromagnetic signatures are very uncertain. Right? So earlier I told you that there you should see periodicities from the accretion disk, or you might see a transient that occurs at the merger, time of merger. But we've never actually seen this. So this is just theory. We've never actually seen this. There's a lot of uncertainties. So that's why I'm very pessimistic about these approaches. The alternative approach that I've been working on is actually looking at the host galaxy. Okay, so earlier I showed you this picture of where you have two galaxies that are merging. You form as a supermassive black hole binary, and then you merge. Do the host galaxies, when you look at the host galaxies, do they look unique in any way? For example, through their morphology or through their kinematics of the stars, their stellar kinematics? Okay, so we started doing this study of what the host galaxies of these supermassive black hole mergers look like using a cosmological simulation of galaxy formation. It's not showing up very well, but I think you've seen videos like this before. These are just cosmological volumes where you have dark matter, you have gas. You stick in gravity, you stick in hydro, you stick in the physics of gas pouring in, and you let it run, and and structures are forming. You form galaxies. And there's black holes in the simulation as well. So when the galaxies merge, you'll get black hole, supermassive black hole emissions. So the specific simulation that we use is called Romulus 25. I will spare you the details, but just know that it contains all the bells and whistles that you expect, like, for example, stellar feedback, AGN feedback, etc. It also includes supermassive black hole growth. And I'll just note that we use this simulation in particular because it is a medium resolution, medium volume simulation. So when you do simulations like this, there's always sort of a trade-off between how big of a volume you're simulating and the resolution. You can either simulate a very large volume, and that's nice because there's a lot of galaxies in that volume, so your sample sizes are large. But if it's very low resolution, and so you're missing a lot of physics. Or conversely, you can simulate a very small volume, and you can do that at very high resolution. So you can capture a lot more physics, but because your volume is so small, you don't form very many galaxies. This simulation is medium resolution, medium volume, and that's nice because if we can get a large enough sample of galaxies, and we can stick in the physics of black hole dynamics. So we're following how black holes actually move when two galaxies merge. So in the simulation, when two galaxies merge, there are two black holes will move around the merged galaxy, and their dynamics are mostly affected by dynamic friction in the merged galaxy. And this simulation has high enough resolution to follow. Okay, so and this is some work led by my undergrad student, Jaden. So we from this simulation, we select a whole bunch of galaxies that are hosting supermassive black hole mergers. So this is what they look like. And we also select a control sample of galaxies to compare to. Right? These are the control galaxies, and these actually look these images look pretty realistic. And they look sort of like observations, and that's because we did we're very careful. We're very careful to make them realistic. So how we create those images, those synthetic images of simulated galaxies, is we do stellar population synthesis and dust radiative transfer. Right. So in the simulation, when a gas particle gets turned into a star, that's a stellar population, and based on the age of that stellar population, we produce a synthetic SED through stellar population synthesis, and then we do dust radiative transfer to get this synthetic image. And then you combine it with the telescope PSF, and then you add noise, etc. You get a pretty realistic image, and so you can then use these resulting images of supermassive black hole merger host galaxies and compare them to the control galaxies to see if there's any unique characteristics. In this plot, I'm just showing you that we're measuring a whole bunch of different morphological statistics, various parameters, morphological parameters to parameterize what the shape of these host galaxies look like. Okay, so these are just a selection of the the morphological parameters that we're measuring from those images. So for example, concentration, just how concentrated is the light. And this is comparing the supermassive black hole merger host galaxies in the red to the control sample in the blue. There's other parameters like the Schuster index, the Gini, which sort of parameterizes how uneven the light is in the host galaxy, M20, which is actually related to concentration, etc. The point here is that when you look at these 1D distributions of these morphological parameters, these supermassive black hole host galaxies, I mean, there's some systematic differences, but they're not that different for any one particular parameter. But what you can do instead is you can combine all of these parameters together into one parameter. And we do that through a linear discriminant analysis. And so through this linear discriminant analysis, you get one parameter, which is called your LDA predictor. And it's actually a linear combination of a whole bunch of different parameters. And this combined parameter gets you much better separation between your supermassive black hole host galaxies and your control sample. And in fact, you get accuracies of up to 90%, which is pretty high. Okay. But okay, so what we've shown is that supermassive black hole merger host galaxies do have some unique morphological characteristics. But what are these morphological characteristics? Part of the reason why we do this linear discriminant analysis is that from the linear discriminant analysis, your results become very interpretable. So this is not like black box machine learning. This becomes very interpretable because it is just this linear combination of your different parameters. And you can plot your different parameters. Like, for example, this is the Gini parameter versus the M20 parameter. In the red here, I'm showing the supermassive black hole merger host galaxies, and in the blue, I'm comparing that to the control galaxies. So these are just the two parameters, two of the parameters that we use. And what I want to highlight here is that this line here is an observational or empirical bulge discriminant. So galaxies that lie above this line have a strong bulge. Galaxies that lie below this line don't have a bulge, and that's from has long been known from observations of other galaxies. Okay? And the point here is that these supermassive black hole merger host galaxies seem to be unique in that they have a pretty strong bulge, right? So, and this is just an illustration, right? So the bulge is the spheroidal component of the Milky Way. Okay, so if supermassive black hole merger host galaxies have a strong bulge, then this would be, you would see it in imaging, right? In the imaging, you would have the strong spheroidal component, but you would actually see it even more clearly in spatially resolved spectroscopy, so in IOP spectrum. Right, so we did a second project where we looked at what the stellar kinematics of these galaxies look like, these simulated galaxies. So this is an image, and this is we create these synthetic data IFU data cubes. This is your line of sight velocity, so you can see redshift, blue shift, right, because the galaxy is rotating. Redshift, blue shift. And this is a stellar velocity dispersion. You can see that there's it's very peaked in the middle, which means that there's a bulge in the middle, has a very strong bulge. So this, and how we actually get these kinematic maps of the stars is we're actually fitting the spectra in each pixel. Right? So in each pixel, we get a synthetic spectrum from the gradient transport. We're actually fitting this spectrum and getting these kinematics. So this is for a supermassive black hole merger host galaxy, as an example. This is for a control galaxy. And you can just see by eye that the major difference is that you can see that the supermassive black hole merger host galaxy have a strong bulge. It's the stellar velocity dispersion is very deep. You don't see that in the control galaxy, but rarely. So they have a strong bulge. However, there's a couple more things, unique characteristics that came out of the stellar kinematic studies, is that these supermassive black hole merger host galaxies have slower rotation and more kinematic misalignments. So what I'm showing you here is galaxy ellipticity, how elliptical the galaxy is. So this is very round, this is very not round. And this is angular momentum of the host galaxy. So this is slowly rotating down here, but fast rotating up there. And these supermassive black hole merger host galaxies are very slowly rotating. Similarly, this is a similar part of galaxy ellipticity versus kinematic misalignments, which is just a measurement of how when you look at the image of the galaxy, you see an axis, and then in your morphological maps. So, for example, this is your axis, and then in your morphological maps, sorry, in your kinematic maps, there's also an axis. Are these axes aligned? So that's the misalignment. That's the misalignment parameter. And you can see that supermassive black hole merger host galaxies are more misaligned.
Run. No.
Yeah, this is my last one.
Okay.
So why is this? It's because these when you have why are there these set of particular characteristics of supermassive black hole merger host galaxies? It's because when you have galaxies that merge, right? So here's two galaxies that merge. When they merge, they form a big bulge. That's how bulges get formed. However, when they merge, they also form a supermassive black hole binary as well. So when you detect a supermassive black hole binary host galaxy, which galaxy is it in the sky? Well, it's whichever one that has a pretty big bulge. So that's why bulges are really important here. During this galaxy merger, the rotation also gets sort of randomized, which is why the resulting host galaxy, the rotation is slow, and also because during the merger, the orbits get randomized, and that's why there's these kinematic misalignments as well. So the overall point here is that supermassive black hole mergers are unsurprisingly related to galaxy mergers. So to find the host galaxy of a supermassive black hole merger, you just look at in that area of sky, you look at galaxies and try to find signatures of galaxy mergers, like large bulges on slow rotation between them. Okay. And these are takeaway points. I won't go through them, and I'll end here.